class, welcome to Fundamentals of Chemistry. I'm Dr. Sujatha Krishnaswamy. In this episode, we'll look at the Bohr's model of the atom. Before we plunge into the Bohr's model of the atom, we're going to take a look at the wave nature of light. So everyone knows that if you turn on a lamp, you get light, but there are different forms of light. Light is a general term that's used for energy. If you want to describe the characteristics of a particle, you would describe how it looks, how it reacts, and we know that those are called as the physical and chemical properties. So if we want to describe light, it is a wave and it is described by three main properties. One of them is the wavelength. Wavelength is the distance light travels in one cycle. So the picture you can see, wavelength is the distance between two identical points on a wave. Frequency is another property that can describe a wave. Frequency is the number of waves completed each second. The third property that describes light, which is a wave, is the energy. Energy is the capacity to do work, and some waves have more energy than others. So with these properties, for example, we can describe the two waves here. You can see the red wave has a much longer wavelength than the blue wave, whereas the blue wave has a much higher frequency than the red wave. So one thing that becomes very apparent is wavelength and frequency are inversely related. Higher the wavelength, lower the frequency. Energy and frequency are directly related. Higher the frequency, higher the energy. So to summarize, higher the wavelength, lower the frequency, lower is the energy. So these three properties can describe any kind of light form or energy. There are many kinds of energies that are known to us, and this is given in the form of a spectrum, which is called the radiant energy spectrum. It's also called a continuous spectrum. It's often referred to as the electromagnetic spectrum. So let's start from the cosmic ray waves. So the cosmic rays have very short wavelengths, so very high frequency and very high energy. Followed by that in the spectrum are the gamma rays, which are also high energy radiation. One definitely does not want to get exposed to gamma radiation. Following that are the X-rays, which are also pretty high in energy. So you know very well that pregnant mothers and fetuses cannot be exposed to X-rays because the high energy can cause tissue damage. Following that is the ultraviolet. And we know that ultraviolet that enters the Earth's atmosphere is responsible for many forms of skin cancer. So ultraviolet is also pretty high in energy. Following the ultraviolet rays in the spectrum is the visible radiation. The visible radiation is a very small portion of the spectrum that excites the retina of the human eye. So we can see the colors in this region only. It doesn't mean the other kinds of light don't have colors. It's just the human eye cannot perceive those. The visible radiation is made up of the following colors. It starts from the violet, blue, green, yellow, orange, and red. There's another color that's introduced between the violet and the blue, and that's the indigo. And that was introduced by Newton because he believed in numerology and wanted an extra number added to those colors. Following the visible radiation is the infrared radiation. It has great practical values. It's used a lot in medicine and forensics and environmental studies. Then comes the microwaves, as you know, used a lot in the kitchen and also in labs to conduct reactions. Then we have the TV and the radio waves. So in this spectrum, the cosmic rays are the most energetic, the radio waves are the least energetic. How does this all relate to the Bohr's model? So let's take a look at the visible spectrum. This ranges from 400 nanometers to 700 nanometers. Nanometers is the unit used to describe the wavelength of these radiations. And this portion of light is what Bohr studied in order to get more information about the model of the atom. We're also going to look at another concept known as a quantum concept. Here are two examples to describe the quantum concept. So one of them is a ball that rolls down a ramp, so it's a continuous roll, and the other is a ball that comes down a flight of stairs. So let's look at the ball that rolls down the ramp. That's a continuous flow. It just comes seamlessly flowing down the ramp. When we look at the flight of stairs, this ball jumps from one stair to another. It can be on one stair, another stair, but never in between. This is known as the quantum concept. So when we take energy, energy is going to be in packets. It's not going to be continuous. It's going to come in small packets. So a packet can have a value, another packet has a value, but nothing in between. These small packets are referred to as photons. So Bohr used all this information about light and quantum concept and photons to come up with his model, which is known as the planetary model. So a quick look at the picture here of the atom tells you why it's called a planetary model. The nucleus is at the center of the atom, just like the sun is at the center of the solar system. Just like the planets go around the sun, here we have the electrons going around the nucleus. According to Bohr, electrons go around the nucleus, orbit around the nucleus in definite pathways. These pathways are known as energy levels or shells. Electrons can be found only in these energy levels. So you could compare these energy levels to a flight of stairs. So the electron could be in orbit 1 or orbit 2 or orbit 3, but never in between. Each of these orbits have a definite energy, which means they are quantized. You can actually calculate the energy for the electron in each of these orbits. So this model, being very similar to a planetary system, is known as the planetary model, or you can refer to it as the Bohr's model. So when electrons revolve around the nucleus in these orbits and they absorb energy, they can jump from one orbit to another. For example, an electron in orbit 1 can absorb energy from the surroundings and jump to a higher energy orbit. And they can jump back to a lower energy orbit. When they jump back to the lower energy orbit, the excess energy is given out, and that can be seen as a color. So when we take the hydrogen atom, which is what Bohr studied, he found that he could see 3 colors: violet, blue, green, and red. He could also correspond to these colors as jumps occurring from level 5 to level 2, 4 to 2, and then 3 to 2. So the electron has jumped from level 2 to level 5 and then jumped back to level 2, and that extra energy is emitted as light, which can be seen as the color violet. What's interesting and a practical application of this is atomic fingerprint. You can see the spectrum for different elements. Mercury has these lines, and sodium's spectrum looks very different from mercury. So the idea is no two elements will have the same kind of electron emissions, and therefore they would not give you the same range of colors. And so this is known as an atomic fingerprint. A practical application of the atomic fingerprint is in archaeology. So if you get an artifact and you want to know what it contains, this is a non-destructive method. You can subject it to this analysis and it'll tell you exactly what elements are present in the specimen, and you can also quantify and come up with the percentage of elements, and therefore you can date it back to a certain era. So these emission spectra of these elements are known as atomic fingerprints. So thank you for joining us today. Hope to see you again in the next episode on the Bohr's revised model of the atom.